When last we met, I had given us our very first definition of physics, and that was the position, the location of an object or an event relative to some coordinate system. A thing that I pointed out that is precious important is that the choice of coordinate system comes first. You must choose the location that is 0, and you must choose the direction that is positive. You must, because it's only in the context of that coordinate system that position has meaning. So that's the first thing you do. And then you have positions. And I was being a little bit of a jokester, and I said that I look at the universe, and now that I have a definition of position, I name all of the positions in the universe. And now I'm done. My physics is over. Ha. Except I close my eyes. While my eyes are closed, everything in the universe changes its position, damn it. And so now I need a new quantity that describes the change in position. And that gave me my first equation. As I said, making a list of equations over here on the right, the displacement, delta x. I learned that the symbol delta means change. And so when I write delta x, that means the change in position. It's very easy to calculate. Delta x, the change in position, is simply the final position minus the initial position. But you have to be careful, because after you choose your coordinate system, the final position or the initial position could be positive or negative. It could be quite strange. You have to use this equation honestly. Choose a coordinate system, put the appropriate numbers in, then you get the appropriate answer. It's entirely possible, of course, that your answer turns out negative. That can happen. Of course that can happen. When your answer turns out negative, it simply means that the displacement was in the negative direction. Imagine I choose things the way I customarily do. That direction is positive here in the front of the room. A negative displacement means I displaced in the negative direction. So the displacement is a new kind of quantity, a vector quantity, a quantity that has a magnitude and a direction. Now, that's what I know so far. Now what I'm going to do is add a level to that. And tomorrow I'll add still another. So I do the same thing again. I stand in my universe, choosing my coordinate system, my location of 0, my direction of positive, name all the positions of everything in the universe, and I close my eyes, and the positions change. Well, here's the thing, strange thing about that. Another observation that I make. When I close my eyes and open them again, some things have small displacements, positive or negative, but the displacement's a small number, let's say half a meter. But other things have greater displacements, 10 meters, 25 meters, positive or negative, it doesn't matter, but large displacements. Some things had great changes in position, and some things had small changes in position. And the thing is, I kept my eyes closed for the same amount of time. And so some things change their position at a greater rate. That is, the change in position happens faster or slower in some cases. So I need a quantity that describes the rate at which I change position. And that quantity is known as velocity. Oh yeah, Scheidly velocity, I get it. Some things have a high speed and some things have a low speed, and so you have to keep track of that. Well, in a colloquial sense, that is everyday language, you probably use the words speed and velocity interchangeably. They mean the same thing in our everyday language. But in physics, they do not mean the same thing. Speed and velocity are not the same. Velocity, like all of my physical laws, has a very strict definition. The velocity of a thing, v, which is also a vector quantity, I'll come to that in just a moment, is the change in position, delta x, which is just the displacement, delta x, divided by the time, delta t, in which that displacement happens. So the velocity of a thing is delta x divided by delta t. That's a new definition that I have. In principle, a new equation that I could write over, right? An equation of physics. It turns out it's not one that I'll use going forward an awful lot. Yeah, we'll go ahead and I'll write it here. That the velocity v is equal to the change in position, delta x, divided by the time in which that change happens. That's the velocity by definition. So what I'll do here is what I typically do when I define a new quantity is I'll write down what the units are. The displacement is the displacement, is measured in meters, because positions are measured in meters, and so the change in position is in meters, and so this quantity is meters, divided by the time it takes for that displacement to happen, which would be measured in seconds. And so our SI unit, if you will, for velocity is meters per second. Notice something really great about this quantity. The displacement can certainly be positive, But it can also be negative. The time is always positive. So far as I know, time is always going into the future. So the time interval is always going to be a positive time interval. If I'm ever doing physics and I get a negative answer for time, I need to go in and check what I'm doing because I've clearly done something wrong, because time is never negative. But the numerator of the velocity could be positive or negative, which means velocity can be positive or negative. What does it mean? Well, it's really quite simple. When the displacement is negative, it means I'm displacing in the negative direction. And so therefore, when the velocity is negative, it means I'm traveling in the negative direction. When the velocity is negative, I'm traveling in the negative direction. Even if I'm on the positive side of the coordinate system, let's say I start here at 5, positive 5, and I go to 4. The displacement is 4 minus 5 is negative 1 in 1 second, I guess, maybe. Negative 1 divided by 1, negative 1 meter per second. I'm over here on the positive side of the axis, but I'm traveling in the negative direction. So it's quite simple. A negative velocity means traveling in the negative direction. A positive velocity means traveling in the positive direction. And the velocity has units of meters per second. Sometimes you'll encounter velocities in different units, more appropriate units. For example, if I'm talking about the behavior of some biological system or a toy or an animal, I might see centimeters per second. If I'm talking about the velocity of a car, I may encounter kilometers per hour. That's another unit that I might get. But my fundamental unit for velocity is always meters per second. Very often I'll find myself converting to meters per second before I do a calculation. Not always, but very often I'll convert. Here's a little trick for you. Kilometers per hour is often the way we metric describe the speed of a car. And there are a lot of cars in the homework assignment. So I'll see kilometers per hour. There are 1,000 meters in a kilometer. 1,000 meters in a kilometer. And there are 3,600 seconds in 1 hour. There are 3,600 seconds in 1 hour. Scheidly, how you know? Well, there's 60 seconds in a minute, and 60 minutes in an hour. 60 times 60 is 3,600. So in order to convert kilometers per hour to meters per second, I would multiply by 1,000 and divide by 3,600. And what I've done for my purpose of solving problems is I've just memorized. It's handy for you to memorize. So you make a little note. I've just memorized that to convert kilometers per hour to meters per second, I divide by 3.6. I've got 1,000 in the numerator, 3,600 in the denominator. That's equivalent to dividing by 3.6. So you might want to make a note of that unit conversion. It'll be helpful in your homework. And this is the velocity. This is the velocity by definition. It is not the speed. It is not the speed. And yet speed is a word that we use very often to describe the rate of travel of things, but it's a very important distinction. So let me define for you speed in physics, and immediately something alarming is going to happen. The symbol for speed is V. But Scheidly, it's a different thing. Why would you give it the same name? I guess in some way, in some small way, we're dumb. Speed and velocity have the same symbol. Isn't that going to cause a problem? Well, it turns out no. Because for the purposes of doing physics, velocity is the useful number. For the purposes of doing physics, velocity is a useful number, and that's really no surprise. Because velocity has both an amount, 5 meters per second, better yet, 340 meters per second, speed of sound. Velocity has a number, but it also has a direction. See, when I use velocity, I get more. I not only get the amount, but I get the direction as well. And so the velocity is a more useful quantity. So I don't have a problem that speed has the same symbol. The speed is equal to, this is critically important, because despite the fact that the velocity is the more useful quantity, we're going to ask you to calculate speed early on here quite a bit. And we might talk about speed quite casually in situations where the difference between speed and velocity is not material to the solution of the problem. As a matter of fact, I may accidentally say speed when I mean velocity. I don't think I'll ever say velocity when I mean speed. But the velocity is the total distance that I travel, divided by the total time it takes to travel that distance. I'm going to give these symbols. The total distance traveled, I'll call D. The distance traveled. The distance traveled is not displacement. The distance traveled is not displacement. Here's why. Consider, please, this little number line that I'll draw here for you, and I'll set the origin here, if you don't mind, and I'll go here, and I'll draw. And now I need some tick marks on this coordinate system. So I'll go 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter, right? So this is 1, 2, 3, 4, 5, 6. And imagine an object starts out here at the 1 meter mark. And then I discover it sometime later that it happens to be over here at the 6 meter mark. right? I have closed my eyes, turned my back on it. It was at 1 meter. Now it's at 6 meter. I'll calculate the displacement. So for a little practice, delta x for this particular case is going to be the final position minus the initial position, which is, of course, 6 minus 1, which is equal to 5 meters. And so I would say here that the displacement is plus 5 meters. And he says, yeah, Scheidly, I don't get it because in order to get from 1 to 6, it had to travel a distance of 5 meters to get there. Oh, no. Nope. Because what you didn't see was that while your eyes were closed, it started here and it went out a ways. It got to 4. It turned around and came back for a bit. Actually went negative and then turned around again and came back here. And then it ended up at 6. Because the distance that a thing travels is the length of the path that it travels. Displacement is final minus initial. You can see clearly here that displacement and distance are not the same thing. And so therefore, velocity and speed are not the same thing. I'm sorry, distance divided by time. I didn't finish my thought there. So velocity and speed, not the same thing. You say, Scheidly, yeah, but there could be. Imagine that it started at 1 and it behaved itself and went directly to 6. Well, yes, that would be a case where the distance traveled and the displacement would have the same magnitude, but the displacement is positive 5 and the distance is just 5. You see, 5 is not a vector quantity. If I tell you that I rode my bike 50 miles, you don't know if I rode 25 miles out one way and then 25 miles back, which would be a very sensible thing to do. Or if I rode 50 miles straight away and somebody picked me up. Or if I just went in my driveway and rode my bike around in a really tight circle until I'd gone 50 miles. You don't know anything about the direction. Distance is a less useful quantity than displacement is because it doesn't tell me about direction. You see that? Okay. Velocity and speed, different quantities calculated in different ways, and so you're going to have to be careful about that. There's another concern that I have, and it has to do with this idea that I know with displacement, I know where I started and I know where I finished, but I don't know what I was doing in between. It's really important to appreciate that these quantities, velocity and again speed too as well, it's true for both of them, that both of these quantities are defined on average. That is, when the object goes from position 1 meter and goes to 6 meters, I can determine its displacement. I can measure the amount of time. But when I use that to calculate a velocity, I don't know that that's the velocity the whole way. Similarly, if I know the distance that I drive my car from here at the school home to my house at the end of the day, and I divide by the time it takes me, I get a speed. But I wasn't going that speed the whole time because there are traffic lights. There's a part where I'm not moving at all. I sit there perfectly still. And there's another part where I'm going 65 miles an hour down the blue route. Happens to be the speed limit, and of course I would not dare exceed the speed limit. And there are other parts in the neighborhood where I'm going at slower speeds as I go. So the speed that I get is the speed on average, not the speed or velocity at any instant in time. Imagine this. You're driving down the road, right? You're driving down Germantown Pike here. And you get pulled over by a cop. Woo! Pulled over to the side of the road. Cop comes up to the window and says, license, registration, whatever. Very nervous, very nervous. Cop says, you're on Germantown Pike, by the way. Cop says, do you realize you were going 85 miles an hour? Try this. No, officer, that's impossible. I've only been driving for 5 minutes. The officer says, you know what I mean. If you had been driving for an hour, you would have gone 85 miles. 85 miles? No way, my mom will kill me. I'm just going down to Wawa. Wawa. I don't recommend that you do that. The next thing that happens is step out of the car, please. And then you're in serious trouble because they don't find it amusing. Velocity defined on average. But strangely enough, on the dashboard of my car, there's a gauge that says I'm going 65 miles an hour. Never faster because I wouldn't go faster than the speed limit. But there's a gauge that says that I'm going. So how does it know? How does it know? Well, that's a serious question. How does the speedometer, how does it work? Magical? Well, that's certainly true. But how does the car know? The car doesn't know where I'm going. It's based on the tire rotation. There's a little gizmo, and it's not really the wheels, but the axle, right? Inside the engine, there's a little part where there's the drivetrain and whatnot, transmission, complicated things, but it's a part that rotates, and it rotates along with the tires. So based on the tire rotation, well, here's the thing. If I'm traveling down the highway, it takes less than 1/10 of a second for the tire to rotate once. Does my velocity change much as the tire makes one rotation? No, it doesn't change much. So if the time interval that I use to measure the velocity or the speed is really, really small, then my value for the speed of velocity starts to approach the instantaneous velocity. And I got news for you all, young science students. That's the reason why calculus exists. Calculus is the mathematics of making the time interval really, 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 really small. So velocity and speed only defined on average. Now the next thing that I want to do is I'm going to take that second equation there, my velocity equation. I'm going to take it out for a spin and see what it can do really quick. See what I can calculate with it by doing a little bit of algebra. This is going to be the simplest thing imaginable. It's the first algebraic derivation that you see me do in this course. The very first algebraic derivation that you see me do. You're going to see me do quite a few of them, this being the simplest. Here I go. I'll start with my definition of the average velocity. The average velocity v is equal to the change in position delta x divided by the change in time delta t. Well, you know that delta x is equal to the final position minus the initial position divided by the final time minus the initial. Look at that. The final time minus the initial time. Final minus initial. The initial time? What's the initial time? Like when you're doing an experiment, don't you start the stopwatch at the beginning? The initial time is very often zero. Very often zero. So very often that it's almost always zero. So for the purposes of this little demonstration I'm doing, I'm going to go ahead and assume that that time, the initial time, is equal to zero. So I strike it out that way. I say let that be equal to zero. So now what I'm saying is that the velocity is equal to x minus x naught divided by t. So my next algebraic step, I'll multiply both sides by t and flip it so that x minus x naught is equal to the velocity multiplied by the time. And then to get where I'm going, I'll simply add x naught to both sides of the equation. That x is equal to x naught plus v times t. And there is both a useful and interesting equation and the answer to the question in math class, when will I use this? Apparently the answer is now. So I'm going to temporarily put this equation over here so that I can use it to solve problems. I say temporarily because later on in our course, I'm going to get a little bit clever and I'm going to replace it with more useful versions. I'm not going to invent new things. Velocity will always be velocity from now on. But I'll replace this equation. Right now, I'm going to do a very, very critically important thing to this equation. Here we go. I'm going to add a bar over the velocity. Ooh, it's too long. Let me redraw it. I'll erase it there. Oh no, oh, it's all gone horribly wrong for me. The bar. I put a bar over the velocity. The reason why is it's critically important that I remember, for the moment, that that quantity is the velocity on average. Later on, I'm going to swap it out for something way sexier, and my physics will become more interesting. But for now, I want to remember that it's the velocity on average. This equation is a great example of a physics equation because it makes it possible for me to predict the future, which is a big part of physics, is being able to predict the way a physical system would behave in the future. I'm a huge fan of talking about how physical equations, particularly my physics equations, are a language that can be read. They're a language that can be read. You can read an equation out loud in words, and it's a critically important skill to be able to do so that you can understand what you're doing. If you decide to be a plug and chugger, you're just going to jam numbers into equations and close your eyes really tight and hope it works out. Well, then I don't know what to do with you. We're not doing physics. We have to think about what things mean. What this equation says is something very, very true. The position sometime in the future will be whatever the position is now plus the average rate of change of position multiplied by time. Notice the average rate of change of position would be meters per second. It's meters per second times seconds, which is meters. It turns out that this quantity, v times delta t, is equal to delta x, just like that. So another way of writing that third equation there, really obvious, is that the final position is equal to the initial position plus the amount by which the position changes. That's a stunningly obvious thing to say. The final position is whatever the position is now, plus the amount of change. And the change could be positive change, or the change could be negative change. Gosh, that makes sense. Just based on these simple ideas and definitions, it's possible now for me to calculate quite a few physics things, and it turns out, solve a few physics problems. The type of word problems that I'm going to ask you to solve are not very unfamiliar to you because of the sort of things that you've already been asked to do in math classes. But now I want you to think about them in a physicsy way as you use the definition of average velocity and speed.